Welcome to another video session on finite element procedure for solving structural analysis problem. In my previous video, I've been solving this particular cantilever source problem using the finite element procedure. I used Matlab to actually solve this problem. I solved this problem with finite element procedure with three different methods on the Matlab working environment. In this video session, I would like to use the ANSYS Finite Element Program to solve this cantilever problem. I would like to demonstrate how we use ANSYS to model Truss structural system and how we obtain results like displacement quantity and axial force in each source element in the structural system. So now I'm going to move to the ANSYS workspace where we will model this problem to get structural analysis results. Before I go to the ANSYS program, I would like to actually explain the problem that we're going to that's going to be solved in this tutorial session. This is a cantilevered source. It is 4 meter. It has 4 meter span. That is 2000 mm, that making 4 meter span. The depth of the source is 1 meter, 1000 mm. We have 3 structural loads at different nodes of the source. We have 0.5 kilonewton load. We have 2 kilonewton load, and we also have 1 kilonewton load. The source is supported at 2 nodes on its left-hand side. The cross-sectional area of each element of the source element is 20.7 times 10 minus 4 meters square. The E is denoting the Young modulus of each element. Constant material. The Young modulus is 205 times 10 raised to the power 6 kilonewton per meter square, or we can say 205 GPa, that is 205 gigapascal. So we are going to solve this problem using the ANSYS program. So I'm going to minimize this PowerPoint screen. On your window search button, you will type Workbench. So I'm using the Workbench 2021 Auto to open ANSYS. So in a minute, the program will come up. Now the ANSYS Workbench work environment is open. The first thing we need to do, we need to activate the static structural solver. This is what we use to solve static structural problem on the ANSYS finite element program. So we right click on this, we left click on this static structural solver on the left hand side of the screen, and we drag it to the middle of the screen and we drop. After we have done this, we need to walk through this workflow from the engineering data to the geometry to the model to the setup, solution, result. The engineering data, this is where we specify the material property of our structural system. So you can double click on this engineering data to open the engineering data interface. So here I'm going to create a new material. I'll define a new material. I'll call it steel. I'm going to type steel here on my keyboard. And I want to add a material property to this new material I just created. And that material property is the isotropic elasticity. It's found on the left-hand side of the screen. So I'll left click on it and I will drag and drop to the steel, the new material I just created. So now I've populated the new material with this isotropic elasticity. If you check just below this table, you'll see the property of outline table for the new material. Each material has its own table. If I click on structural steel, there is a predefined property for this structural steel. This is like a default material which always available by default in ANSYS software. But this is a new material I just created. It was empty before, but I added this new property. So in this new property, we need to define the Young modulus and the position ratio. In our question, we're told that the Young modulus is 205 times 10 to the power 6 kilonewton per meter square, or you can say 205 gigapascal. So I'm going to enter my Young modulus. I want to enter the Young modulus in a unit of gigapascal. So I'll change this unit to gigapascal, enter 205. The Young modulus, I'm assuming my material is steel, and typical value for young modulus, I said Young modulus. The portion ratio, I'm assuming the material is steel, and typical value for portion ratio for steel is around 0.3. You can check that on the internet. The portion ratio specification actually does not affect the accuracy of the results, but you must specify the value. If you don't specify it, you won't be able to perform analysis on the software. So these are the two minimum parameters you must specify in the engineering data to actually solve any problem using the ANSYS static structural solver. So now I've defined my new material as steel. I've defined the Young modulus. I close the engineering data. Now we are done with the material property specification. We move to the geometry. Under this geometry, before we double click on it to open, when we double click on it, an interface called the space claim working environment shows up. That's where we define our geometric model for our structural system. But before I double click on it, you first need to check this role component here, line bodies, make sure it's checked. And also this analysis type, they are actually true 3D and 2D. You can actually leave it at 3D, you can leave it at 2D, but I prefer to leave it at 3D. So my analysis type is 3D, but once we are defining our model in the space claim and we choose linked source elements, we reduce the analysis from 3D to 2D. Because plain source is, if we are analyzing plain source is a plane type analysis. So it's a 2D plane analysis. So I'll leave it at 3D. Then I will double click on the geometric tab. I'll left click, double click on it to open the space claim working environment. This will take some minutes. Now the space claim window is active. So this is the space claim window. This is where we define our geometry for our structural system. So I want to draw along the y-x plane. So I'll click on this button found below. You left click on it. This select new sketch plane. And I will move my cursor. You see, as you move your cursor, the three planes are available for you to choose. I want to choose this plane. So move your cursor in this direction and left click to select the xy plane. Then click on the plane view to bring to the plan view. This plan view button to bring the xy into focus. So my unit for my dimension is in millimeter. So I'm drawing in millimeter. So let's go back to the PowerPoint to know our dimension for our truss. We have 2 meters, 2 meters, and 1 meter, 2000 mm, 2000 mm, and 1000 mm. So I'm going to use these dimensions to specify the geometry of my truss elements. So this is what I'm going to do now. I click on the line, on this line button here, on the top of the screen. I'll start my sketch from the 0, 0 coordinate, the xy coordinates. So I will enter 2000 mm, the first line segment. I'll enter another 2000 mm for the second line segment. I will draw 1 meter, that's 1000 mm at right angle at that point. I will move to the left. I will trace that node point upward 2 meters. I'll do the same thing 2 meters. I return to this point. I'll draw a line from this node to this node, 1 meter. I'll draw another line from this node to this node. I will click on the escape to leave the line command. Do the same thing here from this node, from this node, from this node. These are all the line segments are representing our source elements. So before you leave this command, you actually need to come to the selection type. This selection type, I think selection type, and make sure you choose just beams. If you leave it at all types, it's going to create a plate element for you, which you don't want. So set this to beam. Under selection, set this to beam before you end the sketch interface. So once you have set this to beam, you can click on this check mark. Ooh, we made a mistake. We still have, I don't know why ANSYS drew plate element for us, and that is not what we want. And what you can do, press Ctrl Z on your keyboard to go back to the sketch command. Oof. Okay, I press Ctrl Z actually, and the plate element disappears. So that's one way of actually correcting it. I press Ctrl Z and there is no more plate element. Click the structure tab, check what is on the sketch plane, just line bodies, which is what we want. Okay. So now I've defined my source elements using the sketch line command. What we need to do, we need to attach cross-sectional area to each line type. So what we do, click on the prepare tab here, go to the beam panel, profile. You click on the profile button here. Say we want to define our cross section as circular section. So I'm going to choose circle. So a cross profile has actually been defined in the structural tree on the left hand side. You see this beam profile. If you should open it, you see a circle cross profile. If you right click on it, click on edit beam profile, you can edit the dimension of the circular profile. It's currently set to 10 mm, but we don't know the radius of our circle. Where this parameter is the R parameter denotes the radius of the circle, and it's currently set at 10 mm. We see the circle here in the diagram, 10 mm. So let's go back to our PowerPoint. We're told that the cross-sectional area of the element is 20.1 times 10 raised to power minus 4. So let's use our calculator to calculate the radius of this circle if the area is 20.7 times 10 raised minus 4. So calculator, let's calculate the radius. 20.7 divided by 10,000. So pi r square is area of a circle. So I divide this by pi, and I find the square roots. So this is the square root of this is the radius of the circle in meters, but I'm working in millimeters, so I have to multiply this by 1000. So the radius is given as 25.669 millimeters. So I'll copy this value. I'll go to I'll click on this 10 mm and I will edit it to 25 points. I'll copy and I paste the results to that point. Press Ctrl V to paste result on your keyboard. So now you can see the radius of the circle is defined as 25.67 mm in the middle of the screen. So if I click on this place, you see 25.67 mm. So you can close this window here. This course profile window, you can close it because we have defined our circle. Click on the structure tab on the left hand side. Now we need to apply this circle profile to all our elements. What you need to do, you click on currently set to circle cross profile. You click on this create button to apply the circle cross profile to all the elements. So now, since I've clicked on it, I can select each element and apply my circle cross profile. I'm applying it now. I've clicked on this element. So a beam element has been created because I've attached a cross profile to the line segments. I'll do the same thing here. Do the same thing here. Do the same thing here. I do the same thing here. Do the same thing here. Do the same thing here. I do the same thing here. So now I've converted all my line segments to beam elements. Click on escape on your keyboard 1 or 2 times to leave the create command. Now you notice a new folder has been created in the structural tree, a beam folder. Open it. So you see your beam element that were created. For we need to change the beam element. The beam type is currently set to beam. We need to change it to link source type because we're analyzing source problem. So you can actually do this to you can change the property of the property of all the beam segments at the same time simply by selecting all the beams. Go under the type, click link source. So everything changes to source element. So I've converted all the segments now to source elements. Before we leave this space clean work environment, there's one more thing we need to do. We need to click on design 1 button here in the structural tree. We need to change this shared topology option here from none to share. Very important. Change it from none to share. So we can close this space clean work environment now because we have completely define our geometry of our source structural system. You can close it now. And we go back to the workbench working environment. So you can see on the geometric workflow is checked, indicating that it is properly defined. Now we double click on the model to open the mechanical workspace. This is where we define our mesh, define our boundary condition. This is where we visualize our results for our structural analysis in the mechanical working environment. It will take some time to come on. So now this is the mechanical work environment. Still trying to load. Now the mechanical work environment is fully active. You can see our source elements, but you will notice something that here actually ANSYS broke our source into 4 segments, which is not what we want, but you should set your mind at ease. This will not actually affect the accuracy of the results. You'll still get very good results. So in the mechanical work environment, we need to walk through this workflow in this project in this on the left hand side of the screen. You need to work from the geometry, material, cross section, coordinate system, mesh, structure. The static structure is where we define our boundary condition and the structural load on our structural system. So if you check the geometry, you can see we have just one component. Matlab group all our source elements into one set, which it calls source circle. What do we need to do here? We need to assign our material property to the source element. So once you've selected the source circle, you will see this table here. Under the material, you need to change this material assignment to the new material we created in the engineering data. You see it here as steel. So you assign that material to this. So I've assigned the new material to our source system. So under this material, this material just contains list of available materials which you can use to define your structural model. Currently, we have just steel and structural steel. Move to the next workflow, the cross section. The cross section contains list of the cross section you have in your model. This is a circle cross section which we define in the displacement work environment. Just have just one cross section. Coordinate system, we have just one coordinate system. Two, that's the coordinate system at this 0, 0 node. But you have option of creating other structural system to suit your other coordinate system to suit your needs. You might need to create other coordinate system in some other problem. The mesh, we need to mesh our model, and I normally mesh my model with a element size greater than the length of each of all the with a length greater than with a dimension greater than the length of all of our finite elements. If you should check our model, we have 2000 mm, 2000 mm, 1000 mm. The diagonal elements, they are the longest elements, and their dimension will be around 2500 mm. So I'll just assume an element size of 3000 mm because I want ANSYS to analyze. I'm using a very high value of element size because I want ANSYS to take each element as one finite element. ANSYS software is a finite element software. So if you can define it as 50 mm, 100 mm, but it will take a longer time for the software to compute results. Using one finite element gives the same result as using smaller finite element for Truss problem. This is for Truss problem. I'm talking from experience. So I'm going to set my element size here as 3 meter, that is 3000 mm. The element order, I don't need to be quadratic. Linear is okay. Linear Truss finite element gives me good results, accurate results. So I set it to linear. So that is the setting. That's all the setting you need, and that's all the setting needed in the mesh workflow. So we move to the static structure. This is where we define our boundary condition. So you can click on it, insert. We need to define our support condition at some node. So we create support displacement. So click on displacement. The support we created was applied to this element, but that is not what we want. We want to apply this support to the node. We don't want to apply it to the element. So what you can do, you select the node. So I've selected the node. Click under the geometry, click on it, click on apply. So now the displacement support. The displacement support has been applied to this node. In our problem, you see we have support at this node and at this node. So we need to apply two supports, one at this node, the other at this node. And we need to add, since our truss is in xy coordinates, so the displacement in the xy coordinates will be 0, 0. The z component, you can set it as free. You don't need to set it to 0. I will duplicate this support and I will select this node and apply the displacement tool support to that node. So I've applied the displacement tool support to this node. And you can see it's because I duplicated it, the x and y is already set to 0. Our load, we have 3 structural load on our model. In our problem, we have 0.5 kilonewton at this node. We have 2 kilonewton at this node here. And we have 1 kilonewton at this node. So 500 kilonewton, 2000 kilonewton, 500 newton here, 2000 newton here, and 1000 newton here. So you should know that. That's what I'm going to specify now in the ANSYS software. So click on static structure, right click on it, insert, click on force. We need to apply a load at this node, 500 newton. So select that node, apply to that node, click on apply to apply the force to that node. Define the load by components. The force in the y direction is minus 500 newton. Minus because the load is pointing down. Minus 500 newton. So I will duplicate this node, this force, and I will select this node here, and I will apply the force to that node. And we know that the force there is minus 2000 newton. Select, I'll duplicate force 2. I will select this node and I will apply the force to that node, and the force is minus 1000. The load 1 kilonewton at that node pointing downward. So I've defined our boundary condition for this problem. Now we can define the result we want to see in the solution of portion of this outline 3. So you can click on this solution, insert. You want to see deformation, directional deformation. Currently it's set to the x direction. So I'll also duplicate this directional deformation. I'll duplicate it. I also want deformation in the y direction. You can choose to label, you can choose to rename the directional deformation to anything you wish. So rename based on definition. We click on rename here. So you can just say directional deformation x direction, rename directional deformation y direction. So you do the same thing for we also need to know the axial force in each member. So under beam result, axial force, we want to know the axial force in each member. So you just need to add it. That's all. We want to also know the reaction. So insert probe force reaction. So we have two displacement support, displacement and displacement tool. Displacement is the displacement support at this node. Displacement tool is displacement support at this node. So I will attach the force reaction probe to displacement support. I'll duplicate this and change the boundary condition for force reaction 2 to displacement 2 support. So now these are the results which you can visualize using the ANSYS software. The deformation, the displacement quantity, the axial force, and the reaction values are the supports. So I think I can run this result now to obtain results. So I clicked on the run button. Let's see results. Now ANSYS is done with its analysis, so we can now visualize the result. Visualize the result. Let's click on directional deformation in the x direction. Click on this x coordinate system, the z coordinate system. So to view the source in this form, so we can animate. You can click on this play button here to see how the source deform. This actually how the source will deform. Actually, is deflecting in a realistic manner. So tells us the results might be good just by seeing how the source is deforming. Let me stop this animation. If you want to visualize the deformation component at each node, we can click on this is displaying deformation quantity in the x direction of the source. So you can click on probe to determine the deformation quantity at the node. This is the deformation quantity at the node in the x direction. So these are the deformation quantity. So we can also do this for the y component. Probe, these are the deformation quantity in the y direction. This is deformation in the y direction. In millimeter, the unit is a millimeter. For the area force, let's animate it. From the animation diagram, what can we say about this color plot animation diagram? What can we say? We see that our critical elements, the maximum force, the maximum compression force, the maximum tension force is denoted by red, positive, and the maximum compression force is denoted by blue. So if we check the diagram, where are we getting red and blue? So whereas the members that is turning red and blue denotes our critical members, which we need to pay attention when we are designing when we are doing the structural design, when we are doing the structural design, when we are selecting, when we are doing the structural design. So it shows that we need to pay attention to, let me end it. We need to pay attention to this top element here, the red element, this one, even the diagonal element. This diagonal element is orange. You can see the force is also very high, around 3092 Newton. Even this blue element is like a compression member too. The blue element is close to the deep blue. So we need to pay attention to these four elements while designing. The other are minor, they carry minor, smaller, easier force. These are the four elements we need to pay more attention to when we are designing our source system. So the color plot is showing us our critical elements for this source system. To display the area force for each element, you can also use the probe button here, but you need to uncheck the snap button because I'm not snapping to the node, I'm just snapping to the body of the source element. So we see this is the value of the source force. This is the value of the area force in this element, 536.6 Newton. The unit is in Newton. This is this value 3872 Newton. This is value for this value for this. This is a zero member. Gives us zero. Very correct. ANSYS is very correct because this was zero for this member. This is the value for this, 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 this is the value for this. So this, you can compare this with the results in my previous video where I used Matlab to solve this problem. You see the results are exactly identical. I'm not going to actually validate the results. You do it yourself. Check my previous video and compare these results to the Matlab results. So if you move to the force reaction, this force reaction gives result of the reaction component at this node. So if we should change from graph to tabular data, you can see the value of the force reaction. In the x direction, the force is 9,000 Newton. In the y direction, the force is 1,768 Newton. The resultant is the resultant of these two forces, which points in this direction. So x direction is 9,000 Newton, y direction is 1,768 Newton. The other force reaction at this node, the resultant, the x component is also minus 9,000 Newton, and the y component is 1,731.7 Newton. So this is how we analyze Truss problem using ANSYS Finite Element Program. So I hope you have learned a lot from this video. In my next video, I'm going to solve another type of Truss problem. I'm going to solve this Truss problem. It's a unique problem. Why is it unique? Because we have a roller support. There are few structural software that can solve problems with roller support. ANSYS programs can solve problems with roller support. In my subsequent video, I'm going to show you how we define the roller support in the ANSYS program. And I'm also going to solve this problem using Matlab. I'm going to solve this problem on the Matlab working environment using the finite element procedure. Thank you so much for watching my video. Stay tuned and look forward for my next video on this particular problem. Have a nice day.